welcome back to this to this course, that is Industrial Biotechnology. In the last lecture, I tried to concentrate on anaerobic digestion process, and I told you how this anaerobic digestion process plays very important role for for bring some revenue from the wastewater treatment processes. So that and also I tried to discuss that why the two-stage process plays very important role for this anaerobic digestion process, because if you operate the process in two stages, then you can run the process very comfortably and you will get a lot of useful results. Now I shall give you some application of this process, how different country they are using this process successfully. First, let me tell you this European largest anaerobic digester plant, that is in the northern Jutland in Denmark. They are using 3000 cubic meter per hour. So biogas they are producing the huge amount of biogas. This is the plant they have, and they are using about 250,000 tons of manure. So there is a huge amount of manure they are using here. So you can see this plant has been successfully done. And here I want to point out another thing. There is an industry called Bacardi, and that distillery plant, that is they have the capacity of the bioreactors of 13,000 cubic meter, which is considered as the largest anaerobic digester plant in the world. That has been in operation in that country. Now, if you look at the chemical composition approximately and share biogas, biomethane and natural gas, how can it be comparable with each other? Now, biogas usually contains 40 to 70% of methane and carbon dioxide 30 to 60%. When it is passed through some kind of purification process, what we call gas absorbing carbon dioxide absorption process, then we can produce methane about 99% and carbon dioxide varies from 0 to 5%. The natural gas, if you compare with this with the natural gas content about 75 to 99% methane and alkane, that is ethane, propane, butane 0 to 25%. So it is quite comparable, and this is, I told you, in our country CNG, compressed natural gas, we use for the running the vehicles, that is largely used by the transportation sector and which contains mostly this methane. Now, this biomethane satisfied all the three principles: security of supply, sustainable and competitiveness. Security of energy supply, a strong need exists to minimize the risks of explosion towards the fossil fuel. Price volatility, ensure the security of energy supply by diversifying the existing energy production sources. Sustainability, because since we are using this process from the waste material, so this waste will be available. So this process can be sustainable for no longer period of time. Competitiveness, because promotion of localized production, energy and simulation technology innovative is the key for the development, because here I want to point out that this biogas can have both the applicability for the small scale as well as in the larger scale. So applicability is there, and this is another biogas plant that is located in Germany. This is largely in operation because application, I told you, biomethanation process has several application: electricity generation, heat generation, vehicle fuel and material use. The natural gas is used as a reactive carbon source in the chemical process, as for example fertilizer production, and iron ore reduction process is largely used. So not only the biomethane has tremendous potentiality in the market. Now, this is a table which compared CNG and the raw biogas. You can find out how they can be comparable with each other. So that is how this biogas plays very important role in the world market. Now, biomethanation actually from the waste to the from energy and producing low carbon gas while restoring the soil, because most of the high carbon carbonaceous fuel, when you burn, it produces a lot of particulate matters in the air that causes the environmental pollution, and this is, since it is the lowest hydrocarbon, so amount of carbon emission is very less as compared to any higher hydrocarbon. So it is environmentally safe. Now, I told you that I want to make a comparative study with the chemical process, how chemically if you produce the methane and how it can be comparable with the biological process. Methane can be produced from the coal. I can tell you that this way the chemical route is from the coal, and biological route is from the distillery effluent, that our basis is 10 cubic meter methane production per day. An assumption we have ambient temperature 30 degrees centigrade, specific heat is 1 calories per gram per degree centigrade, H1 H2 is the energy required for heating, and overall loading rate is 10.7 kg per cubic meter per day. Now, this is the process biological process. I told you this is operated in as 2 stages. This is acidogens, this is methanogens. In the acidogenic process, the retention time is 1.5 days, and in the methanogenic process retention is 6 days. Now, this is when distillery effluent comes like this and goes like this. This is how this is the energy required for this. The mixing and pumping is 34 megajoule, and here it is in the form of substrate 4.3 megajoule, and when you get that energy here also we get our gas contains 134 cubic meters. So this is the 2-stage process we operated at IIT Delhi. This is the acidogens, this is the methanogenic reactor, this is the pilot plant we operated very successfully, and we find that the distillery effluent can be very easily used, and we use for the production of methane and carbon dioxide. Now, if you look at the chemical routes, that the carbon, how it is converted to methane, this is 2 carbon. This is by using gasification and methanation. This is the stoichiometry how is produced methane. In partial hydrogenation, this is the stoichiometry that we have. In the direct hydrogenation, the stoichiometry of the process is like this. Now, when you make a comparative study, thermal efficiency of ideal process for conversion of carbon to methane, that the basis is 100 cubic meter of methane production. We have this kind of efficiency here 53.2% in case of gasification and methanation. In case of hydrogen from the hydrogenation from methane, it is this is from carbon it is 65.3%, hydrogen from the product methane. This is like this. I can show you this, the gasification and methanation, partial hydrogenation and direct hydrogenation. If you look at this process, and this process is find much, that is the second process is appear to be the better as compared to other 2 processes. The partial hydrogenation is good as compared to energy point of view, it is quite attractive. Now, that is how we compare this process with the biological process. This is very interesting, that energy content of the substrate in the form of carbon, in case of this coal it is 3.999, this is gigajoule, and in case of biomethanation process in the form of distillery effluent is 4.3. So, that external energy requirement here is 1.205, this is gigajoule, and this is 0.204, because here this process is occurred at the high temperature and high pressure. This is occurred at the ambient temperature, close to the ambient temperature and atmospheric pressure. So, net energy required this plus this will be like this, and this will be like this. And here gross energy requirement means how much energy is required per gigajoule of product. So here we find in the chemical process 0.35 gigajoule of energy required per gigajoule of methane production, and in case of biomethanation process 0.006 gigajoule of that energy requirement per gigajoule of methane production. So this is a very interesting parameter, what we call net utilizable energy product. This is equal to externally utilizable energy minus secondary energy input. This is what we call secondary energy input. So primary utilizable energy, externally utilizable energy is this much, this minus this divided by primary energy available. That if we multiply, if we divide by this, it will 54 point primary energy available in the form of that is the raw materials, that is the 54.9%, and this is 74.3%. That means that the energy that you get in the form of methane largely you can use for other purpose, because here the energy that is you recovered in the form of methane, a less amount of energy is required for meeting the energy requirement of the process. This is how we can justify that biological process is more attractive as compared to the chemical process. Now, other stoichiometry I have, this is the kind of equation that we have, that 1 mole of glucose when you oxidize is we produce 3 moles of carbon dioxide. It produces actually 3 moles of acetic acid, and 3 moles of acetic acid produce 3 moles of carbon dioxide and 3 moles of methane. So if you, and again when you oxidize this methane, then you will get, you require 6 moles of oxygen. So if you convert it, how much kg of methane per kg of BOD, this is how equivalent amount of BOD. This is 48. This is 3 into this is what 12 plus 4, that is 16. 16 into 3 is 48. 48 divided by 192, it is 0.25. That means per kg of BOD removal, actual theoretically production is 0.25 kg. Now, if you multiply it with 22.4 liters, you will get this that we know at NTP 1 gram mole of gas is equivalent to 22.4 liters. Now, if you use that parameter, you will find 0.25 kg of methane is equivalent to 0.35 cubic meter of methane. Now, that this is the equation that we have, that is the what is the E is the efficiency of waste utilization. Normally the range from 0.6 to 9% under the satisfactory operational conditions. Now, Q is the, I told you that suppose this is the process, suppose this is the anaerobic digestion process, and you are passing a Q is the flow rate and S0 in the substrate. So, what is the unit of Q? Q is the volume per unit time, and what is the unit of this mass per unit volume. So, if you multiply it Q into S0, it is nothing but mass per unit time. So, now if you multiply it by utilization efficiency, that is E, then what will happen? E, if you multiply it, this is multiplied by E, then how much of this biomass can be converted into gas, that you can find out. And you have already seen that 1 kg BODU can produce 0.35 cubic meter of methane. So, if you multiply by this, you will get how much methane is produced. Now, problem is that when you consider this conversion process, I told you this substrate, a part will go for the methane and carbon dioxide, and a part will go for cell mass production. So, cell mass that remain in the system. So, when you say the conversion, so that cell mass amount of energy that stored in the form of cell mass, that also you have to minus. So, this is we have already seen one, for the oxidation of 1 gram of cell mass, you required 1.42 grams of this the oxygen. So if you minus with this, then you will find that what is the exact amount of methane is produced per kg of waste. This you can calculate. Now this is the equation. This is the rate of cell mass that formation. It can be expressed like this. This is the formula that we have, and this is the typical kinetic coefficient of the anaerobic digester of various substrate. We have used the domestic sewage, we have fatty acid, carbohydrate and protein. The value yield coefficient and specific death rate constant, they varies from each other, and the table shows the mean cell residence time, what we call solid retention time at different temperatures will be different, because you can see that how it varies with respect to, because more temperature high, this will be reduced because your organism will be more active. Now I want to solve one kind of problem, that is very much useful for anaerobic digestion process. They estimate the size of digester required to treat the sludge from a preliminary treatment plant designed to treat 38,000 cubic meter per day of wastewater. Find out the volumetric loading, estimate the percent stabilization and amount of gas produced from the waste water to be treated. It has been found that the quantity of dry solid and BOD removed is 1.15 kg per cubic meter and 14 kg per cubic meter respectively. Assume the sludge contain 90%, 95% moisture. It has the specific that gravity is 1.02. Other pertinent assumptions are given below. You have to find out that. So first we shall have to find out the sludge volume. We have already seen this is here. It is dry solid that dry solid contains is 0.15 kg per cubic meter. So here and this is the flow rate. If you multiply it by this, you will find that what is the total amount of sludge is there. It contains 95% moisture. So you divide by 0.05, you will get the wet mass, and the wet mass has the density is 1.02 into 100 kg per cubic meter. If you divide by that, you will get the volume of the sludge. And then similarly you can calculate the BODU loading. This is to be removed, that is given digester volume. You can easily calculate by Q into theta C, that you can find out that that what is the how much cubic meter of multiply that how much, what is the volume of the digester, you can easily find out. Then volumetric loading is how much total solid we are putting in the reactor divided the volume of the reactor, that you can find out the volumetric loading, that per unit volume of the reactor how much solid material you are putting in the reactor, that is considered as the volumetric loading. Now rate of production of the cell mass can be expressed like this. I have already shown, and this value is like this. Percentage stabilization, this is the substrate removal efficiency, how much substrate is removed, and this is the how much substrate that cell mass present in the reactor. If you minus this, then you will find that actual amount of BOD that is removed from gas formation, and this is the input of the substrate. So if you divide by that, you will get the percentage stabilization. That is how you can calculate 76%. The rate of methane, we have already this equation. You put the different values in the equation, you will get the how much methane is produced. Now if we assume 2/3 of the gas is methane, we can find out the total gas what is produced in the system. Now I want to share with you a very interesting thing, what you call landfill gas generation process. Now because this process is largely in operation in the western country, and unfortunately that in India it is not in operation, because every country generated lot of solid waste every day, and if you look at per capita production of the solid waste in the cosmopolitan cities is much higher as compared to the village. Village is quite less, because it has been observed that the amount of waste that is solid waste generated by per person per day, that also determine the economic status of the people. I can give a very typical example. in case of USA, the per capita production of the organic waste, municipal solid waste, is about 2 kg. But if you compare the cosmopolitan cities in India, it is around close to 0.5 kg. So that indicates the kind of economic status of the people, and it is huge. But one thing we should remember in our country, that we have our number of population is very high as compared to the Western country. So even the per capita production is very less, but if we multiply it with the number, then it will be total amount will be very high. So what I want to point out, the availability of the raw materials is very high. Now second, that is the important factor in the Western country, that kind of municipal solid waste they are generating, they mostly containing the tissue type of material, tissue papers. And tissue paper, as you understand, that tissue paper mostly comprises of the cellulose. It does not have any kind of nitrogen source. So your organism, when I explain the growth of microbial or microbial cell in a particular media, we not only require the carbon source, we require nitrogen source, we require minerals, we require vitamins. So if your nitrogen source is very less, your growth of the organism will be affected to a great extent. For that, so you have to fortify. Fortify means you have to put some kind of nitrogen source with this waste material, so that the bacterial growth can take place properly. Now if you compare the quality of municipal solid waste generated by the Western country and that of India, most of the solid waste that we generated, it contains the vegetables. And as you know, in the vegetables not only contains carbon, but it contains good amount of nitrogen. So we don't have to supply any kind of nitrogen source here. The whole raw materials is good enough for the bacteria to grow. But only the problem is that in India we are not following the international sanitary law. Now international sanitary law says, suppose this is the downland where you put your waste like this. So if you post any kind of solid waste, that within 24 hours this should be covered with 6-inch clay layer. This is 6-inch clay layer. Why? Because the reason is that they observed within 24 hours the biodegradation will take place, and since the biodegradation take place, a lot of bad gases will comes out to the atmosphere and it pollute the environment. So to safeguard the environment within 24 hours, it should be covered with 6-inch thick clay layer. So like this, you can have another layer, you can have another layer, you can have another layer. Like this, you can fill up your landfill. This is the international sanitary law. Now what is saying that at the end, when it is totally filled, then it is totally covered with, then it is thick. It will produce maybe 18-inch layer. It produce thick layer that you put, so that ensure there is no gas going out from the system. Then what they do, they make a well. This is the pipe, perforated pipes we put inside inside this. So we put different perforated pipes here, and these perforated pipes we interconnect this. We can make the interconnection of the perforated pipes, and if we make little bit of vacuum in the line, then what will happen? Whatever gas is producing, that will come here, and this goes like this. And this gas mostly contains methane and carbon dioxide. Then we passes the carbon dioxide absorption column. We remove the carbon dioxide, we get pure methane. So this is largely in practice in the Western country, and after the stability of this process, they can use this landfill for the beautiful preparation of beautiful park, beautiful playground and amenity centers. They can have very, but only the disadvantage of this, that nobody can build up the multi-story building here, because the soil quality is not good as normal soil. So it is because this we consider as a very fertile land. So you can have a very good park, good and playground like this. Okay. And this I was thinking about how best we can utilize the this municipal solid waste in India. And I was considering that that if you look at the age of the landfill is 5 to 10 years, and 5 to 10 years is pretty long time. So we did some kind of work, research work, just to find out how this time can be reduced. Because I told you already, the acidogens is very faster, rate of reaction is very fast as compared to methanogens. So what we did, we carry out this reaction in the acidogenic reaction on a particular reactor. Now here we build up the solid bed, and here we sprinkle the acidogenic culture. We recycle this again and again. We can recycle this again until and unless the stabilization take place. When we find that this bed is totally stabilized, then the liquid we pass through the methanogenic reactor. So that, so what is our suggestion was that, suppose we consider this is because here I want to point out one thing, that as the time passes on, in the cosmopolitan cities, the lands are very costly. So if we find that as the time passes on, most of the downland that will be filled with the waste material. Now they have to go to the distant places. So what you call the hauling distance, they increase drastically. As the hauling distance increases, the cost of transportation increases to a great extent. Our suggestion was that if you can identify one particular land in a particular cosmopolitan cities, and we can, if we divide the land in suppose 1, 2, 3, 4, 5, 6, 7, 8 like this, and different wells we can have, and we put the raw materials in different one after another, and that, and we find through our research work, we find for the stabilization of this reactor we hardly require 40 days. So if we keep 40 days here, the organic material will be totally stabilized. Then we can fill in such a way that when you come here, then here might be 40 days, then you start vacating this land, and this digested material you can take it out, use as an organic fertilizer, and whatever liquid is there you can pass through the reactor and produce methane and carbon dioxide. In the outside you can pass through the reactor and produce methane and carbon dioxide. So this is largely can be used. This is kind of solution that we have, and this is how industrially the landfill is operation. This is the screening, that that it is the weighing truck comes, then we take the weight, after unloading we take the weight, then we find out how much waste was there, then we pass through the shader, magnetic separator, then we put it in the landfill, then we recycle this, we take it the liquid out, pass through the methanogenic reactor, we get methane, and sludge can be used for as a fertilizer. So this process largely, and this is how it looks, that in methane recovery, how we can, I told you the pipe we can interconnect it, and we can apply the vacuum and take the gas out. We can remove the carbon dioxide in the processing plant, and we can have SNG pipeline here, or SNG CNG vehicles. We can store, we can load here, or can use for the generation of electricity. So it has very vast vast potentiality that we have landfill. And when I had the opportunity to work in Timarpur landfill area in Delhi, and we find that that lot of because we don't follow the international sanitary law, that is why the gas is going out from the solid material, and you will be surprised to know that I observed at least 30 to 35 pockets through which I constantly observe the flame, and when I ask them how the flame is burning, then they are saying that all the truck driver, when they come for unloading their waste material, they might be using some cigarette, they throw it out, and since methane is coming out, when they come in contact with the methane, it gives the flame. And in the night it looks like Deepavali, because in a whole land you have a lot of, so we are wasting lot of energy. So that if we can, so we should think very seriously how fruitfully we can utilize that, then a lot of energy we can use for the human benefit. So in conclusion, I want to point out the anaerobic digestion has been found lot of potentiality throughout the world, and it is not only useful for the industry, it is useful in the domestic sector also, for the individual family, for some community, for municipality. They use the organic material for the generation of biogas, which can be used as an energy source for running vehicles and other things. So with this, let me conclude this. Thank you very much.